This is the 8th lecture in the review section before we start Algebra 1, and today we're going to talk about prime factorizations, and I know that's a big word, factorization. And all a factorization is a multiply sentence that equals a number. For example, 4 is 2 times 2. That is a factorization of 4. Now, there's several factorizations of 8. How about, 2? Well, actually, there's one. There's 2 times 2 times 2 times 2, and then there's 4 times 2. What about 12? 12, you could do 3 times 4, or 2 times 2 times 3. What is the difference between these two factorizations? Well, if you look closely at this, each of the factors are prime, and that's what makes it a prime factorization. So a prime factorization is a multiply sentence that equals a number where all the factors are prime. So to do this, we're going to remember our divisibility tricks from the last video. And then we're going to break numbers down using a factorization tree and find the prime numbers. So the first one we're going to look at, let's do the prime factorization of 20. And 20 is 2 times 10. And then we're going to keep breaking these down until each of these numbers are prime. If you remember, some of the prime numbers were 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. They probably won't get too higher than this. So breaking down 20, 2 is prime, so I'm going to circle 2, and 10 is not prime, 10 is composite, so we can break 10 down further into 2 times 5, and 2 and 5 are both prime, so we can write 20 as 2 times 2 times 5, and this is the prime factorization of 20. How about we do 36? Okay, there's several ways. Now, there's several ways to break down 36, just as there was you could have done 4 and 5, and you would have still got the right answer. Because, and I'll get to it, each of these prime factorizations are different for each number. All right, so two numbers that multiply up to be 36. The easiest one maybe is 6 times 6. You could do 9 times 4. Let's do that. Let's prove that they're the same here. Let's do this as 9 times 4. Okay, and 6 is 2 times 3, and 2 and 3 are prime. And 6 is 2 times 3, and 2 and 3 are prime. Now over here, so 36 is 2 times 2 times 3 times 3. But we're not done over here. Let's break down 9 into 3 times 3 and 4 into 2 times 2. And you'll see all those are prime there. And they're all the same. They're the same. So no matter which numbers you break down first, you're going to come up with the same number. How about we do a bigger one? How about we do 84? Because I don't think that a lot of people know how to break down 84. Other than 84 is 2 times 42, and 2 is prime, and you may know that 42 is 6 times 7, and it just so happens 7 is prime, and 7 is 2 times 3, and 2 and 3 are prime. So 84 is 2 times 2 times 3 times 7. Now, you don't have to put these in numerical order, but it's a good idea when you use them, because we're going to be using them in the future. In the next lectures, especially, we're going to be using these. So always try to get into a habit of putting them in numerical order. Okay, so let's talk about what I was just talking about, how each of these are unique. That is the fundamental theorem of arithmetic. The fundamental theorem of arithmetic. And that is each composite number has a unique prime factorization. Every number is different. What about prime numbers? What about 7? 7 does not have a prime factorization because it is prime. So you would just say 7 is 7. Okay. One more thing I want to look at. How about 110? Numbers that end in 10 are easy, and a 0, because you could say that this is 10 times 11. And 11's prime. It's on that list. And 10 is 2 times 5. So if it ends in a 0, I always break out that 10 first. Okay, so 110 is 2 times 5 times 11. Okay. One thing I want to do before we close this out, because that's all this lecture has in it, is prime factorization, is talk about using exponents to represent prime factorizations. And we haven't really talked about exponent. But to remember, in an exponent, we have a base and an exponent. Okay, we're going to call the base A and the exponent B. And we would say that this is A to the B power. And what this means is we're going to take A and multiply it by itself B times. So 2 squared is 2 times 2. 3 squared is 3 times 3. So it's 3 multiplied by itself twice. So why is this relevant to prime factorizations? You may want to save yourself some time, or you may be asked to save yourself some time in the future on a test. If you find the prime factorization, let's find the prime factorization of 441. Okay? 441. And I know that 441 is 21 squared, but you might not know that. I always try to recommend that you memorize your squares. So instead of breaking it down into 21 times 21, I'm going to say, assume that you don't know that. I might assume wrong, but you can add these up, and they add up to 9. So that means it's divisible by 3. So what happens if we take 3 out of 441? What are we left with? 3 goes into 4 once, and then we have 14, and 3 goes into 14 4 times, and then we have 12, and then 21. 3 goes into 21 7 times. So it's 3 times 147, and 3 is prime. And if you add up the digits again on 147, you get 1 plus 4 is 5, and 5 plus 7 is 12. So this is divisible by 3. And we just kind of did this part right here, right? 3 times 4 is, it goes in, 3 goes into 14 4 times, remainder 2. And we're left with 49. So this is 3 times 49. Now I do think that you should be aware that 49 is 7 squared. And 7 is prime. So 341 is 3 times 3 times 7 times 7. But you may be asked to see it like this. 3 times 3 is 3 squared. Times 7 is 7 squared. Okay, so that concludes the lecture on prime factorization. Lecture 9 is going to be the greatest common factor and the least common multiple of 2 or more numbers. And I will see you then. I appreciate you watching. See you next time.